All right, so today I'll be continuing on what we started yesterday with the tutorial on self-supervised learning, but this time with more focused research talks around some of the latest work that we've been doing on the field. And this work in particular is collaboration I did with Brayan and Jorge, which are in the Universidad Industrial de Santander in Colombia. And the paper is on archive if you want to have a look. So let's start. Again, I'm going to be speaking about inverse problems. I went over this yesterday, so I'm not going to go in detail, but we have measurements related to an underlying signal X or an image that have been corrupted by forward operator A, and we have noise corrupting those measurements. And this noise here it's additive, but we'll see that I'll be extending to non-additive noise problems. So one more time, as yesterday, what we want to do is build a self-supervised or unsupervised loss, which basically the goal is to have something where which is proportional or shares the same minima as the supervised objective, and the supervised objective we'll be considering, but not only this one today, will be the squared loss. So which is kind of the standard in imaging. And as we saw yesterday, again, this can be written as a sum of a measurement consistency and an important term, which is the correlation between the prediction f of y, so the output of a denoiser or a neural network, and the noise. So here, today's talk is going to focus mostly on denoising problems. So again, most of my talk will have A as identity, forward operator as identity, although most of the results can be generalized when A is invertible. And we'll see what happens as well when A is not invertible. So I'm going to be placed in a setup where we assume that we know what the noise distribution affecting the measurements is, but this noise distribution will often be non-Gaussian. This is the case of many imaging settings, like low photon imaging, where the noise is generally Poisson, or quantum, or well, any type of signal photon avalanche diode type of imaging, where we have either Poisson or binomial noise. And if we go to remote sensing, often in synthetic aperture radars of STAR, we observe gamma noise, so multiplicative noise. Okay, but although not being Gaussian, we kind of know the noise model in these applications. Okay.
What's the SPAD?
That's a good question. A SPAD is something that can measure kind of one photon at a time in a simplistic way.
Single photon, something.
So photon avalanche time. So basically, you can detect individual photons. And we have a group in engineering in Edinburgh that makes cameras, arrays of these things that can detect very, very low light imaging, basically.
Yeah, and the city of Edinburgh, I think south of Scotland in general, is like a war leader.
Yeah. So if you look like at this SPAD type of image, will look like that because you just accumulate photons one by one as they come, but you will have very, very sensitive imaging compared to CMOS cameras. Okay. And if we want to learn from, so I would be assuming that we have multiple observations of this type of images, so a data set either of noisy SAR images or a data set of SPAD images and so on, and we want to learn to reconstruct them in a self-supervised way, okay, with no ground truth data whatsoever. And yesterday we saw that for denoising, one of the key results was Stein's lemma, which basically says that if the noise is Gaussian distributed. This term, this correlation term that we need to get rid of is is equal in expectation to the divergence of the function, okay, which doesn't require x at all. And we saw that we can minimize thus this Shor loss, which is a measurement consistency plus the divergence. Okay, where second term, as I said yesterday, is capturing the degrees of freedom of the wobbliness of the denoiser. So this, because it approximates the supervised loss, it will give you, if you have sufficient data, the optimal MMSE estimator. And if we want to go away from Gaussian and we want to now do the same but for Poisson denoising, have an SPAD camera, what we can use is Hudson's lemma, which basically extended some of the results of Stein to other types of distribution. Most of them all of them in the natural exponential family or in the exponential family. And for example, for Poisson noise, the exact formula looks like this, where we see that we have, there is no derivative here, and this kind of makes sense because in Poisson noise, y will be a discrete, so an integer value, right? Because it's the number of photons we observe. So it doesn't, f is not really taking a continuous random variable anymore. Okay. So here I'm assuming that the Poisson model has gain gamma over there equal 1, but this can be generalized for gain gamma not equal to 1. But the point is that f is something that takes an integer. The denoiser takes integers, and so you should do it like that. There's no divergence. But this is very expensive if you want to evaluate it. Why? Because you would have to evaluate the denoiser f, removing one photon per every pixel and recomputing the output. So this would require evaluating f n times, where n is the number of pixels. So very, very not computationally tractable if n is large. Yes.
What is EI?
So EI is like removing in the ith pixel 1. So it's the canonical vector. So what people do in practice is to say, well, we can take a Taylor approximation and say the ith output, so Fi, will just take this Taylor approximation over here, and then when you plug it in the thing on the first line, you'll get that something that you only need one evaluation now, which is kind of a weighted divergence. Okay, where it's almost the same as the Gaussian case, but now with y instead of sigma squared. The thing is, this is a strong approximation, we'll see, and generally it's a bit suboptimal because we are taking an estimator f that is supposed to take integer values, and we are assuming that it's somehow differentiable. Okay.
Sorry, so you find in practice that it's.
Yeah, we'll get to experiments later, but yes, in practice there's a massive difference.
Oh.
And so you can use this approximation to now build Shor estimates for both Poisson and Gaussian noise. And in both cases, what people do in practice, although it's not the only way of doing it, Bernard does it's using autograd, is by taking finite differences instead of doing the and the way you would do it is add a bit of noise and multiply accordingly with this Monte Carlo estimate. So yesterday we saw that there's also another family of methods which also require knowledge of the noise distribution, which do this magical trick, right? Whereas, which basically we take one noisy image y, and we generate two of them, y1 and y2, that are conditionally independent given x, and that share the exact same mean. Okay, and the proof is like very simple. If you want, I can do it over here. We have y1 equals x plus epsilon plus tau omega, y2 equal x plus epsilon, maybe I should put myself like this, minus omega over tau. Okay, and what we want to show is that these are conditionally independent. So I need to show that the expectation, because they are.
That if you go on the other side, it's not.
Sorry. So we need to show that these are Gaussian random variables conditioned on x. And so if we want to show that they're independent, the only thing we need to show is that the correlation is 0. Okay, so we'll just do the y1 minus its mean. The mean is x. Okay, in both cases, times y2 minus its mean. Okay, so this gives us the expectation over omega and epsilon of epsilon minus tau omega times epsilon plus omega, sorry, the plus and this is the minus, like this. All right, and then we get, so this thing over here, the cross terms are 0 because these are two independent random variables. The only ones that stay are the quadratic terms. Okay, so we get this thing to square minus tau over tau, which cancels out, expectation of omega squared. So if these two random variables have the same variance, this thing will be 0, and these variables are not correlated. They're independent because they're Gaussian. So this is a strong, quite a useful probability trick that I feel is not that known in the community, but very simple to show. And so using these results over here, as I wrote on the board, these things will be independent. So when we compute the cross term that we want to get rid of for doing the self-supervised loss, we will get 0 because we get that this expectation over here is has 0. Is 0. Okay, so we can just train on going from one of these extra noisy copies to the other, from y1 to y2. And this is kind of the noise to noise, if you remember from yesterday, but we have created our two noisy copies ourselves. So we end up with two algorithms. We have the recorrupted to recorrupted on one side, okay, which is using this trick, and Shor with the Monte Carlo divergence on the other side. Both require knowing the noise distribution. So if you look closely, they kind of look very similar, right? Both are adding some omega, both have some tau over there, but they have some differences. So what do they have first in common? They both require tau positive, and they both require omega to be sampled with the right variance, the same as the noise. But the nice thing about the recorrupted to recorrupted is that you need a single function evaluation to compute it, although we will have to take the expectation over omega to have the proper thing. In practice, we only do single omega randomization. And on the other side, you need two function evaluations. But on the short side, we have extensions to Poisson and other random variables, and on this side, we didn't really have that. Okay. So what I try to tackle here is do extensions for Poisson and so on of the one on the left. In order to keep these nice properties, we need a single function evaluation, and we'll see also that we'll get something that is not an approximate extension, but the correct extension. Yes.
So you're saying that you only need obviously these are Monte Carlo, so these are an expectation of omega. So really we need to know what the variance of the two estimators are to know how many approximations. If I want to compare apples with apples.
Yes, yes, they have different variances, and we're not going to speak about that today, but I can point you to some.
Okay, thank you.
So I'm gonna be extending the recorrupted to recorrupted to the whole natural exponential family. So the natural exponential family are noise distributions that can be written in this form, which when you look at it might be a bit scary. There's a lot of terms over there, and you'd say, well, this doesn't look like Gaussian, for example, but after careful definition of eta and phi and h, you will find that this takes into account the Gaussian case, but also takes into account the Poisson case, the gamma noise case, the binomial noise case, and so on. They all fit into this setup of natural exponential family. Okay. And something to be careful with is that this is not the exponential family. There's little difference between natural and exponential family. Okay. So sorry?
What are the last two rows?
Yes, this will be my two new random variables. I'll come that in a second. So to extend the theorem that I did before, I'm going to change tau for alpha. I will explain why that's in a minute. But we can do something very similar as what I did with Gaussian here on the board for the whole natural exponential family distribution, where we separate our y into two noisy copies y1 and y2 such that they add to y after weighting by 1 minus alpha and alpha. And there's two important properties. They will have the same mean as y, so x, if the mean of y is x, and they will have variances that scale with 1 minus alpha and alpha, and I come back to that in a second. But the key thing here is that they will be independent conditional on x, the same as before. Okay, and the only thing we need to know is how to sample y1 given y, because y2 can come just with solving this equation. Okay, very simple. So in the paper, we write the formula for a general natural exponential family, but it's more useful to look at expressions for distribution that we know. For the Gaussian case, so I had used tau, which is over there, but it's just a reparametrization of alpha. The nice thing here is that now alpha, before tau was positive, any positive value, now alpha is something between 0 and 1, so it has a very clear meaning. And depending on how I choose alpha, we put most of the variance into one of the random variables, or most of the variance into the other one. Okay. And we'll see that, yes, the Gaussian case remains exactly the same up to reparametrization, but then, for example, in the Poisson case, we see that this is just not adding more noise, as one would naively think. It's resampling the noise. For example, if we have observed Z photons, we have to sample a binomial random variable with some probability, which will put some photons on y1 and the rest of the photons on y2. The same is for gamma, but this time we'll resample an auxiliary beta variable and separates y1 and y2 in a multiplicative way. And something similar is for the binomial with the hypergeometric distribution. This is always for sampling y1. y2, once you know y1, comes just by solving the formula above. Okay, so we end up with a general way of doing these losses over here. Here I'm doing the expectation over multiple realizations y1, y2 given y. And because these two are independent, again, we can do our little trick of separating the loss and showing that this thing here is 0. So so our self-supervised will be exactly the same in expectation as the supervised ones. And here there's something important. I'm doing the expectation condition on x. So this works for a single image. Doesn't even have to average over the whole distribution. Here we have another constant term, which is actually proportional to the variance of y, but when we are just thinking of training over f, this is a constant, and so we get our desired results. Yes.
Do you see this as significantly different from bootstrapping?
It's an intelligent way of bootstrapping.
Because if let's say you have a Poisson random variable, but if that Poisson random variable comes from having counted events, the way of bootstrapping, the non-parametric bootstrap, what it would do is it would randomly select a proportion of those.
Yes,
events.
In that case, I think they
do like cross-validation. So it feels as if you are unpacking the sum in a random way, and if you have the list of events as opposed to the sum,
yes,
like a non-parametric bootstrap would do essentially the same.
For the Poisson case, I agree. For the gamma case, it's kind of you're unpacking a multiplication, so it's slightly more involved. But yes, in the Poisson case, I think you can probably find some equivalence. A nice
or as you say, this is sort of like a more sort of like elegant and principled way of motivating.
Yeah, that
like a bootstrap heuristic.
Indeed, yes. And so now we can think about the role of alpha, okay, which I said is between 0 and 1. And if we define the SNR as, so the mean squared over the variance, we'll get that the SNR of y1 is alpha times the SNR of y, and the SNR of y2 is 1 minus alpha the SNR of y. Something important is that because there's no free lunch, we cannot increase the SNR by doing this trick. We'll just reduce the SNR because we're kind of adding more noise. But how much more noise we are adding? Well, it's a trade-off. We will put more or less noise in one of the random variables and the opposite on the other one. Okay. So since we generally input y1 into the neural network, we don't want to choose an alpha that is very. Sorry, I think I flipped them here. It should be 1 minus alpha on top and alpha below. But we want to choose an alpha that doesn't reduce the SNR too much on the inputs. And so we will choose an alpha that goes to 0 because these are swaps. And but if it really goes to 0, the SNR of y2 becomes infinite because it becomes 0. So we need to find a trade-off. Something also that it's nice about this trick is that it extends very naturally to other losses that are not the L2 loss. And when we are fitting something that is not Gaussian noise, we can think about Bregman divergences. And the most natural one is to consider the log likelihood. So here is the log likelihood of y2 given x. Okay. And so we can write this log likelihood like this, and we'll see that again, this due to the properties of Bregman divergences which are related to the natural exponential family. So any log likelihood of a natural exponential family random variable will separate very nicely, and again we'll do our trick where we can separate y2 and y1 that are independent. So we'll end up with something that is in expectation proportional to the supervised log likelihood, where we put, so this should be x and x1. This is when you do the slides in the morning very quickly. And something that is proportional to the log likelihood. Okay. So you're probably wondering, okay, what do we get if we minimize the log likelihood versus minimizing the L2 loss? Well, the nice thing is we get the same. So we will get the MMSE estimator in any case. So the posterior mean, given y1, not given y, just y with a bit more noise. So the minimum is the same, but for a realistic setup where we don't have infinite data, that expectation is a sum over a finite number of samples, we can imagine that maybe the log likelihood perform better than the L2 loss because it captures better the shape of the distribution of the noise. Okay.
Yeah, it's asymptotically efficient. I mean,
it's asymptotic.
Long lived.
So is it obvious that it's the same?
The proof of why is the same. I mean, it's just an intuitive way of thinking is if you are doing maximum, if you're doing an MLE estimator with no regularization, generally the MLE estimator is just x equals y. And that's when you think it in learning boils down to having the exact same estimator as the MSE. But the proof it's on the paper is it's a bit more, it's not obvious. But so yes, in the real world where we'll be using finite number of samples, we will have more efficient estimator by using this. Which is something that did not show up in Shore, right? In Shore, we did not see this link we were just approximating the L2 loss. And so this gives one more line to my table where we can do the negative log likelihood loss for each of these different random variables over here. So there's something to remark here in practice. These logs can be a little bit unstable with neural network training. So although the theory tells you should use this one instead the L2 loss, where in the Gaussian case, of course, they match because the log likelihood is just the L2 data fidelity term. In these ones, we'll see that often they work better and often no, depending not. So it's not that clear. And we have now what I feel like is the nicest, well, the more interesting result of this work, which is that actually we can show that all of these we can see Shore as a limiting case of the generalized R2R. So if we take now the L2 loss and not the log likelihood one, and we take alpha going to 0, sorry again, the white one, y1 and the first line are swapped. We see that the noise that we are adding in the inputs is going to 0, and the noise that we are adding to the target is going to infinity, but we're doing an expectation. So these things counteract each other, and we end up with results that shows you that you can do, that in the limits you are doing the exact same as Shore with the true divergence. The nice thing about this is that this recovers exactly the Poisson and the Gaussian case. But for example, for gamma, I did not know any Shore loss for gamma. It does exist, it's just that it requires higher order derivatives, and this is probably why no one was doing this. But it's also a way to recover Shore losses automatically.
I'm thinking again about the MLE. So when you train with the L2 loss, you train to get the posterior mean.
Yes.
Which you expect will be optimal in mean square error. Well, the meaning when you were saying, this is the MLE, so it's asymptotically efficient. Yes, but I'm starting to marry the sort of like asymptotic efficiency of the MLE, which seems like a good idea with the posterior mean. And the posterior mean seems to be a better estimator. I mean, they're kind of like optimal with respect to two different random variables. The MLE is optimal for y given x, and the posterior mean is optimal for x given y.
Yeah, I mean, we need to be careful when mixing ideas from MLE estimation and learning, because here we are optimizing over F, so I don't think some of them can be a bit.
They can be misleading.
Misleading, yes.
They carry automatic.
But yeah, but it's a good point.
Also, I'm not sure how much the asymptotic regime kicks in when you train this kind of models. Anyway, it's interesting.
Yes.
So I wanted to know if I don't know, is there any assumption related to the dependence of the noise on the signal or on the measurement, or it holds in any case. Like, for example, in Poisson noise in low count imaging, where the noise is signal dependent. Is the result still or
Yes, yes. So this is the Poisson noise where the noise is signal dependent. So in gamma, the noise is also signal. In all of them, the noise is signal dependent, except for the Gaussian case.
But it's only for denoising. Like right now, it doesn't hold for declaring.
Yes, it doesn't hold for declaring, although I'll do the extension in 1 minute if I have time. I don't know how I'm off time.
It's okay.
Okay. So okay, how do we do this in practice? Well, in when we are training a reconstruction network or just a denoising network in this case, we will we'll get one noisy image from our data set. We will split it into two using one of the formulas in the table according to the noise distribution that we have at hand. Then we will put one of them as the input of the network and the other one we will ask it as a target, and just training from this one to this one because they are independent is the same as training as if we had ground truth. Okay, so that's relatively cheap during training because we'll do only one random split, so we just do one evaluation compared to short, and then at test time we will, because we are adding this extra noise to generate y1 given y, we can average over as many as we want. And so we generally over J, and now I would say what J is a practical value for doing in practice. So what happens again, as we saw yesterday, if we have incomplete operators? So if they are not invertible, if they're invertible, everything I explained still holds. If they are not, it doesn't, because we have a null space. So even though we can denoise very well in the range space of the operator, we might still have a bad reconstruction on the null space because we're not penalizing the reconstruction over there. So as I said yesterday, we can do covariance imaging. So that is imposing that the whole imaging chain is equivariant to a group of transformations like translations or rotations. So this is the same as yesterday. I'll go quickly. Again, as yesterday, the loss is just imposing the equivariance of the imaging system. But the nice thing that you can do, and I need to find new names because I keep calling it robust equivariant imaging plus plus plus, is mixing the GR to R loss with the equivalent imaging one. So these will handle the noisy measurements, Poisson, gamma, and binomial, and so on. And this one will take care of the null space. So let's look at some experiments. This is for Gaussian denoising. So this set is the same setup as the original Recorrupted2Recorrupted paper. Here we obtain a performance that is almost the same as short. But the nice thing is that we train faster because we just need one evaluation of F per epoch. And we are very, very close to supervised denoising for all noise levels. More interesting is the case of Poisson denoising. So this is for different gamma levels where gamma will control how much Poisson noise we have. So it's interesting to see that if we have gamma very small, will mean that the noise is smaller in a way and it's closer to Gaussian, so the central limit theorem will kick in. So we see here some of the asymptotic properties of the MLE estimator, in the sense that if we have something that is closer to Gaussian, the MSC loss, the L2 loss will perform the better. And when we get something that is very low photon, very Poisson-like, using the negative log likelihood version works better. And it works, all of them work better than the Sure version, which is called Pure for Poisson. And they work particularly better in the case where gamma is 1, so we have lots of Poisson noise. because in this case, the approximation I mentioned at the beginning with divergence is particularly bad. And we can get performances that are very, very close to the supervised, even for very low Poisson case. So gamma denoising. So in gamma, we will have a parameter L, which is the number of looks. And if L is bigger, we'll have something that's closer to Gaussian. If L is smaller, we'll have something that's closer to gamma. So again, we see something similar, although in this case, the negative log likelihood is not performing that well as expected. And for this case, we didn't have a sure competitor because the formula is too long and too ugly. But it performs better than doing, for example, cross validation, as we saw yesterday with the neighbor-to-neighbor loss. And it can handle. So these are real SAR synthetic aperture radar images. The final experiment is if we have an null space, so a bit of a toy problem imaging painting, and in this case with Poisson noise. And so we can do equivariance imaging with the Poisson GR2R loss, and we get something that is very close to the supervised case again. Whereas if you do equivariance imaging with just the measurement consistency and not taking into account the noise, it will not work, of course. So two final results. Mike was asking yesterday, what is the optimal alpha I should be using? Well, here it is. It's I think 0.1. So it depends on the problem. It seems that for Gaussian 0.2 or 0.3 it's an okay choice. For gamma, we find that 0.1 it's a good choice, and in Poisson it's 0.1 as well.
In any case, it seems to be quite compressed or something, right?
Yes. You don't want
to
get
alpha a bit wrong. You don't want to put 0.8, right?
Yes.
0.2, you're kind of.
It's not super. Yes, not super important. Which it's for people who have played with Shore, this tau parameter can be a bit cumbersome to choose, whereas here alpha has a more intuitive meaning.
Is this for a single realization?
So this is for a single. Yes, for a single data set per problem. So
you're doing a single core call to
yes,
per image.
Yes.
And presumably, if you change that, then you make it a difference.
I think if you add more averaging over losses, I would expect this to move to the left. So how many averages at test time? So we try this empirically. So if you just do one random evaluation, you're gonna lose white stone performance like 0.4 dB. But then after more than 5 or 10 averaging some resampling images, it's not improving massively. So a little bonus before where Marcelo will be speaking about this more in detail, but this I think is quite exciting that this GR2R actually works for a single image. So all the unbiased estimation results work for a single fixed X. So we can imagine using this for doing some bootstrapping or uncertainty quantification, where we sample these pairs of noisier images and as kind of bootstraps, and we provide a distribution of error estimate by looking at the distribution of this. So that's it. Thank you. Sorry?
Is there a link between the EY given X and the omega distribution? Or is it just like Poisson to beta? Brayan and Self-supervised? Is that something like conjugate?
It's a good question. I skipped some of the technical details over here. So the theory also tells you what's going to be the marginal distribution of y. So in all of these cases, the margin is the same as the original one. So like the marginal of y is still gamma, the marginal is still Poisson, and so on. And this one is generally not matching the distribution. So like Poisson is binomial, beta is gamma is beta, and this thing you just get it by writing the formula. And
There's no other relationship.
no, and they are not these are not in the natural exponential family. They are in the exponential family, but not in the natural one. So they're not necessarily even.
Conjugate priors.
It's similar to the idea of conjugate priors, although, like for example, for Poisson, the conjugate prior is gamma, and it's not.
Yeah, no, they're not. Yeah, they're not. So, how do you start to think about the fact that there is a form of invariance here that you're using? So, a lot of these distributions are they are what they call divisible distributions.
Yeah.
And you're kind of like sampling all random variables y1, y2, subject to the constraint that they have to add up to y.
Yes, this is how we prove the theorem. So yeah, there is even in all this theory the idea of divisible random variables, which we're saying y divides into y1 plus y2, and we want some of y1 and y2. Yeah.
So you're essentially, but of course you implement it through sampling, but it's almost as if you are, you're integrating over all the combinations of y1 and y2.
When you do the expectation, yes.
Yes. Is it somehow imposing that your estimator needs to respect some form of invariance or
to having less photons?
Not having less photons, but it's.
But it's, yeah, I see the point.
Thank you for the presentation. Is there any risk that the method overfit with respect to the corruption strategy, so that it can have a certain sort of a fake conversion?
So these are independent, really. So we didn't see any overfitting because the one of the noises, although it looks like the neural network tried to overfit this noise here, it really can't because it's independent from that one. So it's, even though you're asking it as a target to target the noisy image, because it has never seen that noise, you cannot overfit.
And what happens if the noise is purely measurement dependent?
In all of these cases, it's measurement, like it's not additive Gaussian noise, so it's intensity dependent. It's dependent on X, but here the neural network is conditioned on X that we're thinking. So although they share the same mean, the random part we want to get rid of
It's independent.
It's independent, yes.
Well, in fact, you could probably show that, maybe you showed it already, that it will overfit less in the sense that the main problem is not so much overfitting to the noise, it's overfitting to the data set.
Yeah.
Like if you are in a smaller sample regime, this is probably going to be more robust to memorizing your training examples.
Yes, definitely, yeah. Yeah.
So your results from Poisson were with the Poisson, I think.
The correction.
This one.
Yeah. So you said it's pretty good for when the Poisson noise level is 1, but actually even at 0.1, it's pretty good. Is that because the Shor model is essentially just? Is the Shor model equivalent to a weighted Gaussian?
Yes. Exactly.
So that's the same as the classical approximation used in CT, and that's known to be only good for the sort of high photon count.
Exactly. putting the covariance.
Exactly. Yeah.
Yes, if we look at this formula over here, or even, sorry, this one, this is the same as saying sigma I is yi. So it's that typical approximation of a Poisson by its putting the variance for the observed value, like the people using CT.
So if I didn't know what the gamma was, can I use this to? I mean, so not wanting to pre-advertise the next talk, but could I use this instead of the divergence term in a trade optimization?
Been thinking the same.
Okay. And okay, one final.
Unreconstructed.
Yeah, you have to.
I'm sure about.
Yeah. I mean, you're saying so in the example show, are you doing the 5 realizations of your generalized R2R of your evaluation? You said at the end that basically 5 was a good number to do. So again, in terms of apples versus compared to apples, in the Shore, you're presumably, although
you're doing 1, yes.
Yeah.
But you're adding tau is generally much smaller than alpha.
Yeah.
Like you just choose 0.01.
So I guess my engineering question is, someone wants to apply this to make lots of money. Which do you tell them to do? Do you tell them to do the Shore, or do you tell them to do the generalized recorrupted to recorrupted?
You do this one,
Yeah.
You don't do the Shore. No.
No. You do the
okay, that's just a specific slide.
yeah.